Length of plane curves. How do we find the length of a curve? Well, we can use the distance formula to find the length of any line segment from some fixed point x equals a to another point x equals b. But for a general winding curve, such as y equals sine of x, we must use calculus in order to determine its length. Given a differentiable function, y is some function f of x, the length of y from x equals a to x equals b is given by the following formula. The length L is determined to be the integral from a to b of the square root of 1 plus the derivative of y squared with respect to x. Given a differentiable function x as a function of y, then the length of x from y equals c to y equals d is given by the formula length is equal to integral from c to d of the square root of 1 plus the derivative of x squared with respect to y. In the first example, we're asked to determine the length of the curve y equals x to the 8th power from x equals 0 to x equals 1. We'll use the formula for y given as a function of x. Because the formula requires the square of the derivative, we'll first start by finding the derivative of y. Well, the derivative of x to the 8th is 8 times x to the 7th. Then we'll square that and find that y prime squared is equal to 64x to the 14th. Plugging this value into the formula, I get that the length is the integral from 0 to 1 of the square root of 1 plus the derivative squared, and we found that the derivative squared was 64x to the 14th. Now I can evaluate this integral using the calculator. I'll access the Math menu, I'll select option 9, then I'll input the function, the variable of integration, the lower limit, and the upper limit of integration, and find that the length of the curve is approximately 1.7203. In the second example, I'm asked to find the length of the curve y equals 127 times the quantity 9x squared plus 6 to the 3/2 power from x equals 3 to x equals 6. I'll again use the length formula for y given as a function of x. I'll start by finding the derivative of y. To compute that derivative, I need the chain rule. The chain rule says the derivative of the outside times the derivative of the inside. Then I'll simplify and find that my derivative is equal to x times the quantity 9x squared plus 6 to the 1/2 power. Then I'll square that derivative and get x squared times the quantity 9x squared plus 6. Distributing the x through the parentheses, I end up with 9x to the 4th plus 6x to the 2nd. Now I'll substitute that into the formula in the place of the derivative squared and find that the length is equal to the integral from 3 to 6 of the square root of 1 plus 9x to the 4th plus 6x squared. Rearranging, that's the square root of 9x to the 4th plus 6x squared plus 1, and that trinomial factors as the quantity 3x squared plus 1 squared. The square root and the second power essentially cancel, and I end up with 3x squared plus 1. And so I find those antiderivatives. The antiderivative of 3x squared is x to the 3rd power, and the antiderivative of 1 is x. And now I'll use the evaluation theorem to evaluate that definite integral from 3 to 6. Evaluating, I'll evaluate at the upper limit 6, and then subtract where I evaluated at the lower limit 3, and I end up with 192 as the length of the curve. Using the calculator, I would arrive at the same result. Thus, the length of this curve is 192. Our final example, I want to find the length of the curve x equals y squared plus 2y from y equals 0 to y equals 2. This time I have a curve where x is given as a function of y, so I'll use the length formula for x as a function of y. I'll find the derivative dx dy. If x is equal to y squared plus 2y, then dx dy is equal to 2y plus 2, and I'll square that and get the quantity 2y plus 2 squared. Substituting into the length formula, I get that the length is the integral from 0 to 2 of the square root of 1 plus the quantity 2y plus 2 squared. Expanding the square of that binomial, I end up with the square root of 1 plus 4y squared plus 8y plus 4, and if I evaluate that using the calculator, I get that the length of the curve is approximately 8.268.